Good morning and welcome to the 2012 Royal Tyrrell Museum Speaker Series. Today the Royal Tyrrell Museum and its cooperating society are proud to present Dr. Mikael Siverson. Mikael is a curator of paleontology at the Western Australian Museum in Perth, Australia. Mikael pursued his undergraduate studies at Lund University, where he obtained a bachelor's degree in geology with a specialization in paleontology and sedimentology in 1989. His honors thesis was titled Paleospinacid Salacians from the Late Cretaceous of Kristianstad Basin in Skåne, Sweden. Mikael received his PhD in vertebrate paleontology in 1993 from the geology department at Lund University. The focus of his PhD work was sharks and rays from the Cretaceous and Dannean deposits in southern Sweden. Following his PhD, Mikael continued his research and also worked as an exploration geologist in Western Australia. Since 2007, he's been working as a curator of paleontology at the Western Australian Museum. During his scientific career, Mikael has described 1 new family, 8 new genera, and 17 new species of Cretaceous and Paleocene sharks and rays. Mikael has conducted fieldwork in England, Sweden, Denmark, Russia, in the Saratov province, Australia, the U.S., in particular the states of Kansas, Wyoming, and Montana, plus Morden, Manitoba, woohoo! And Poland, Germany, Israel, Egypt, and France. He is organizing annual field expeditions to more or less remote areas of Western Australia to explore that vast area for Mesozoic vertebrates. Apart from working on fossil sharks and rays, Mikael has also published on dinosaurs, believe it or not, describing the first ceratopsians from Europe, and I think that was with Phil Currie. He's also described the first Mesozoic mammals from Scandinavia. He's worked on numerous mosasaur projects, Cretaceous turtles, and it's too bad Don can't be here to appreciate that, pterosaurs and plesiosaurs. Today, Mikael will discuss the current knowledge of the fossil record of Lamniform sharks, their diversity and timing of their evolution and ecology, in a talk entitled Lamniform Sharks, a 110 million years of ocean supremacy. So without further delay, I present to you Dr. Mikael Siverson.
Thank you. The talk I'm going to give is about the Lamniform shark. Now this is probably the most well-known of all Lamniform sharks, the white shark. Now I'm from Perth in Western Australia, where we have beautiful beaches, but every year, especially in the spring, in October, we are reminded of the fact that we don't rule the oceans once we step into the water. I think we had 3 fatalities off the beaches of Perth within a couple of months last year. One of them was one of the main beach, Cottesloe Beach. White sharks can certainly be dangerous animals for swimmers and snorkelers. But today we're going to talk about the rise and fall of various apex predators in the oceans, looking back 110 million years. At any given point, there's always going to be one species that is dominant. And in many coastal environments today, the white shark is the dominant apex predator, certainly in temperate areas of the oceans. However, it is not the ultimate apex predator in the ocean. That title goes to the killer whale, Orcinus orca. There are a few cases of predatory interaction between orcas and white sharks that have been documented over the last few years, and the orca has always come out on top. It appears that the orcas have developed a special technique to handle larger, potentially more dangerous sharks. They sort of flip them upside down, which basically immobilize the shark, and then it proceeds by just holding the white shark in that position for a few minutes, and then it can just start to feed on the shark. It's predominantly the liver that the orcas are after. there are other species of sharks that orcas prey upon. So basically today, the apex predator in the ocean is the orca. There's no other species that we know of that preys on orcas, but they prey on virtually all other species, including the largest toothed whale, the sperm whale. They don't seem to attack adult bull sperm whale, but they certainly attack females and juveniles. And it's easy to understand why the orca is such a successful predator. We can look here at the most impressive set of teeth, about 10 to 14 teeth in each part of the jaw. Very, very robust skeleton and very powerful jaws, and a formidable predator. The males can grow to at least 9 meters in length and weigh around 7 tons, so they are very, very large animals. And the reason they are able to dominate the white sharks is, part of the reason is, well, they are pack animals, but also they are bigger, quite a bit bigger. In those cases, there was one case where 2 female orcas that were observed attacking a 3 to 4 meter white shark, but the orcas would have been maybe around 5 meters, but quite a bit heavier than the white shark. But let's go back in time to the, the talk's going to cover the lamniform sharks of the last 110 million years, but let's go back to the late Jurassic. This is a pliosaur referred to as a Predator X. It was discovered in Svalbard, Norway, and during the late Jurassic and well into the early Cretaceous, the pliosaurs, they were the killer whale equivalents. They were the apex predator. Huge animals with a head up to about 3 meters in length, and they could reach 10, possibly 12 meters in length. I'm not sure if you watched the BBC's Walking with Dinosaurs, where there was one pliosaur featured there, Leoplerodon, exaggerated the size of that animal. That's quite common in paleontology, as we all know. Someone finds a small part of the animal, maybe a single vertebra, and then they extrapolate that into huge dimension. In this case, Leoplerodon was estimated up to 20-25 meters, but it turns out that was based on a caudal vertebra of a sauropod dinosaur. So it's shrunk quite considerably since then. In Australia, we have Kronosaurus, and that was one of the biggest pliosaurs, possibly the biggest pliosaur in the early Cretaceous. It's particularly well known from Queensland in northeastern Australia. And it was a very large animal. It could grow to about 10 meters in length. And for up until now, there was no dispute regarding the apex predator position within a large inland sea that's now in the Eromanga Basin, Great Artesian Basin in Queensland, in the early part of the Cretaceous, Aptian Albion, where we have the large inland sea, not too dissimilar to the great Western Interior Seaway of North America. This is just to show you an outcrop in Western Australia. Later in May, Mike Newbury and Todd Cook, they're going to come with me, and we're going to explore these rocks. We see here is a sandstone, it's a 30 meters sandstone unit, and at the top we find remains of extinct marine reptile, including rare bones of this giant Kronosaurus. So we know that it occurred also outside of the Great Artesian Basin along the western margin of Australia as well. Back in the early Cretaceous, Western Australia had just separated from what's now referred to as the Greater India. That's a part of India that is now being pushed under Asia, forming the Himalayas. And on top of the Windalia sandstone member, which is Aptian in age, we have other units in the Albion, and on top we have a chalk of late Cretaceous age. This is one of our volunteers exploring the Wendalia sandstone member. We always bring volunteers on a field trip, very much the same as here in Drumheller, I'm sure. This is one of our best volunteers. He just found a vertebra of an ichthyosaur. One problem being a vertebrate paleontologist in Western Australia is that the area is deeply weathered. We don't have the same kind of uplift as we have in many parts of the central North America. So it's been very deeply weathered. It's just a passive continental margin. So those areas where we do find vertebrates, for example, like in Kalberry, there's almost always a calcareous cap rock preserving the bones. In other areas, they tend to be leached out. This is the most complete plesiosaur that's come out of the Wendalia sandstone member. Well, it's actually a composite of 3 different individuals, but it gives you an indication about the state of preservation. It's not too bad, but it's in a sandstone, so you don't tend to get perfect preservation. But on the other hand, there is no deformation. It hasn't been covered by a really large amount of sediment, so the 3-dimensional shape is still intact. The head is missing here on this particular specimen. It's a smaller pliosaur. There we are. This is the Tyrrell anticline, which is situated just north of Shark Bay. It's an anticline. In the center you have Aptian sandstones, and then it gets younger as you move towards the legs of the anticline. And this is from a field trip where we were exploring the Geel siltstone, which is an Albion to Cenomanian marine unit. When I first came over to Australia in 1994 as a postdoctoral fellow, I started looking for sharks in the mid-Cretaceous deposits. And the general idea is when you find a fossil shark's tooth, you can sort of figure out the size of the whole shark by comparing it to the teeth of modern species. For example, if you find a tooth of a white shark, an anterior tooth approximately 3 centimeters tall, that corresponds to a shark roughly 5 meters tall. So based on that knowledge, I kept finding isolated teeth here, maybe up to 3.5 centimeters. I thought that probably came from sharks roughly 3.5 meters. This is just to show you a section of the Geel siltstone, this Cenomanian unit. Part of the problem doing field work in Western Australia is the spinifex. That's a very sort of a prickly plant that grows here, so when you sit down you have to make sure you don't get them up in your bottom. So it can be quite painful doing field work there, actually. Yeah. But this is a very typical sort of area in much of Western Australia, sort of like a bush desert. Western Australia is a huge state, the largest in Australia. But we have the beautiful shark's teeth. This is an undescribed species of a genus called Dwardius, found as it was, well, it's a little bit staged, this photograph, but just a little bit. We've got some belemnites here and gypsum, and the shark's tooth. This is the Geel siltstone. So I kept finding these teeth, and one day in 1996, I was walking along the outcrops looking for fossil shark's teeth, and my wife was sitting reading some women's magazines. She was a little bit bored, but she decided to come along. So we were walking along the outcrops, and suddenly I see a shark's tooth on the ground. And curiously enough, that was a species I had described in a paper I had just submitted a few months earlier. So I was quite excited about that shark because I wasn't quite sure where it fit in the Lamniform systematic. And then my wife picks up a vertebra, and it's absolutely humongous vertebra, much bigger than I would have imagined that tooth would belong to. This is the excavation pit where we excavated this shark. It turned out that it comprised, the whole specimen comprised more than 100 teeth and more than 15 vertebrae. These are some of the teeth. These are upper jaw teeth. It was published in 1999. Cardobiodon was a new genus and a new species, even belonged to a new family, the Cardobiodontidae. These are the vertebrae. They are up to about 90 millimeter. If you compare it to the white shark, the vertebrae of a 6 meter white shark would be roughly about 100 millimeters. 6 meters is the maximum size of white sharks. There are plenty of reports of bigger white sharks, but once you start to scrutinize those records, they all fall apart. So 6 meters seems to be the widely recognized maximum size of white shark. That was caught in Western Australia, by the way. So they have very large vertebrae, much bigger than I thought they would be for teeth of that size. So this is my attempt at reconstructing the dentition of this Cardobiodon shark. And given that the teeth were smaller, one of the things that I did discover was that it had a larger number of tooth files, which makes sense since the tooth, the mouth, the relationship between the size of the mouth and the length of the shark is more or less fixed in these lamniform sharks. So the modern species appear to have a smaller number of tooth files in the lamnids, for example, the white shark. So there seems to be a general trend where you have a reduction in the number of teeth, so the shark can grow larger teeth. And this is just to show you the size, the circumference here of the lower jaw teeth of this Cardobiodon shark compared to the lower jaw of a 2.5 meter long fin mako shark. So it's a big shark, this Cardobiodon. A couple of years ago, someone sent me an image of a Lamniform vertebra from the Darwin member. It's an Albion, sort of lower Albion unit near Darwin in the Northern Territory in Australia. And the remarkable thing about it is its huge size. It's 125 millimeter across. And I'm just here as a comparison. This would be a vertebra from a record-sized 6 meter white shark. So it's much bigger. And again, that's totally unexpected. Prior to my study on Cardobiodon and the discovery of these vertebrae, we didn't really think there were humongous sharks in the early Cretaceous. But it appears that the sharks in the early Cretaceous, these Cardobiodontid sharks, were the biggest sharks of the Cretaceous period. That has obviously profound implications when we try to reconstruct the food web, because the pliosaurs have for a long time been regarded as the undisputed apex predators in the early Cretaceous seas. A couple of months ago, someone notified me about additional vertebrae of this Cardobiodontid shark from a unit called the Tullibuk Formation in Queensland. Now, the Tullibuk Formation is a basal upper Albion unit, well known for beautifully preserved ichthyosaurs and other vertebrates. In the Tullibuk Formation, it's a dysaerobic deposit. You often have laminations, and the only invertebrate fossils you tend to find are inoceramids. So there was a poor circulation with occasional bottom water anoxia. The remarkable thing about these vertebrae is their size. Now remember, this vertebrae was about 25% larger than a vertebra from the record-sized white sharks. Now these are even bigger. These are about 145 millimeter across, which is nearly 50% larger than those of the largest white shark. So we might be dealing with lamniform sharks up to 8 or 9 meters, weighing possibly as much as 7 metric tons. That's potentially heavier than the weight of the giant pliosaurs, Chronosaurus. They were portrayed in TV programs as weighing up to 120 tons or something. but that was based on the sauropod vertebra. So they have shrunk considerably. I think they're down to 3, 4, 5, 6, 7 tons. So it might be that these sharks were actually the heaviest predators in the early Cretaceous. And this is another Lamniform shark, a carabidontid, again from the Tullibak Formation. And you can see here the number of articulated vertebrae. It's a specimen that I'm doing some research on together with Mike Newbury and Todd Cook. And it's a specimen in the Natural History Museum in London. So by looking at the vertebrae, we can section the vertebrae, we can look at the growth patterns of these sharks, we can learn a lot more about these giant predators that no one really even knew existed. These are the teeth, some of the teeth. They're quite robust, indicating that they had a heavy set of jaws. But they are much smaller than teeth of, for example, Cretoxyina, which is a well-known shark from the Upper Cretaceous. A little bit smaller shark, but had bigger teeth. So it seems like these giant sharks increased the size first, and after they reach a certain size, 6, 7, 8 meters, then over a few million years, they started to reduce the number of tooth files so they can grow larger teeth. But the interesting thing is that the pliosaurs could not hold back the giant sharks because they were at least as big as the pliosaurs. At the Cenomanian-Turonian boundary 92 million years ago, we have something referred to as the Oceanic Anoxic event number 2. We had record high sea levels, increased volcanic activities at the plate boundaries, and as a result of these increased movements of the plates, you get more iron and micronutrients released into the oceans. And the flooded continents that hadn't been flooded for a very long time, you get a lot of organic material washed out into the oceans. And you also had high levels of CO2. And that basically is as you're pouring fertilizers into the ocean. So you had massive algal blooms. And when these algae decayed, they consumed the oxygen. So we get these black laminated bands. Wherever you look on shelf deposits, lay down below maybe 130, 140 meters, you have this bottom water anoxia. That had a severe impact on the ichthyosaurs, these fish-like marine reptiles. They had very big eyes. In fact, some of them had eyes slightly bigger than those of a blue whale. That indicates that ichthyosaurs were deep divers, so they were feeding on something that lived rather deep, probably some form of cephalopods. So the ichthyosaurs died out, but the big giant sharks, they all survived this crisis. The pliosaurs were already in decline, and a few of them survived into the Turonian, but I don't think any one of these large giant forms extended beyond the Turonian, so they went extinct. So now the Lamniform sharks were the undisputed top apex predators in the ocean. This is just to show you the section, the Cenomanian-Turonian boundary in Kalbarri, Western Australia. These sediments are a bit lighter colored. They've been oxidized. We have drilled through this section further up in that basin, and you get the very dark, typical boundary layer between the Cenomanian and the Turonian. But we can see here some distinct laminations. Normally on a well-oxygenated shelf, you have lots of burrowing organisms that will destroy this primary lamination. And if we look at the shark fauna down here, we have plenty of bottom-dwelling sharks, rays, and once you got here, they're just gone, completely gone. And all you get is pelagic species. So you could argue that if you continue to produce, increase the CO2 in the atmosphere, we might eventually produce another anoxic event. It is possible. And if we look at the shark fauna, we get in these laminated beds, we get an awful lot of teeth from a shark called the bramble shark. Now, prior to my work on these outcrops in Kalbarri, This genus was known worldwide by about a dozen teeth of Cretaceous age. You can see there's hundreds, if not thousands of them. So they occur in huge numbers. They are probably, this particular genus seems to be more tolerant to low oxygen levels. So probably picking off bony fish that might have ventured too deep into the Anoxic-Oxic interface. I mentioned that some of these large apex predatory sharks, they survived the Cenomania-Turonian boundary. This is one of them, Crotodus crassidon. This is an undescribed specimen from Italy. It has a big turtle in its abdominal cavity, very massive shark, almost a meter across here at the jaw, and very big, heavy teeth. It was the dominant apex predator in shallow water once you get into the later part of the Cenomanian and into the Turonian. It survives into the Centonian period. So it was the apex predator in shallow water environments, at least in the tropics and subtropics. The dominant apex predator in offshore environments, however, was Cretoxorhina mentali. It's very well known from numerous specimens found in the Smoky Hill Chalk of the Niobrara Formation in Kansas. It was the most formidable shark. We know that some of the specimens probably could grow to 8, possibly 9 meters. They were a little bit smaller in the Western Interior Seaway, but in offshore, normal marine environments, you find really large individuals. This is the Smoky Hill Chalk in Kansas. So basically, you have the large pliosaurs die out around 100 million years ago. A few of them survived a bit longer. So lamniform sharks had now ruled the oceans for approximately 15 million years. But there's a new type of predator rising, and that's the mosasaurs. These lizards, ocean-going lizards. They are very well known from numerous specimens in the Smoky Hill Chalk, and you also have them here. There's a beautiful prognathodon on display in the museum here. I like this image. That's a mosasaur, by the way. The dominant offshore apex predator Cretoxorhina certainly didn't give up without a fight. This is actually based on an actual specimen. I think it was a platycarpus that was found that had been bitten in half by a giant Cretoxorhina. And this is based on specimens from the Smoky Hill Chalk. And this is a part of the section. Must have regurgitated the specimen soon afterwards. There you are. There's some teeth still stuck. This one. Oh. There you are. However, remarkably, as it may seem for me who works on these magnificent lamniform sharks, the mosasaurs managed to rise and take over the apex position, in particular the Tylosaurians. This is one famous Tylosaurian mosasaur called the bunker mosasaur. It's a Tylosaurus. Cretoxorhina died out around 81 million years ago. So for nearly 30 million years, we had giant lamniform sharks in the 6 to 9 meter range. But now they're all gone. Instead, the mosasaurs developed huge predators growing up to maybe 13, 14, 15 meters. And remarkably, the lamniform sharks did not produce any new giant species throughout the reign of the mosasaurs. So the mosasaurs reigned as supreme apex predators of the oceans from about 80 million years till they died out at the end of the Cretaceous period for 15 million years. So for 15 million year period, the lamniform sharks didn't get bigger than maybe 3 or 4 meters. They didn't challenge the mosasaurs. However, at the end of the Cretaceous period, the mosasaurs go extinct. Several of the shark lineages go extinct as well. I think about 50% of all genera of sharks and rays go extinct at the KT boundary. One particular lineage of lamniform sharks, the Octodontids, survived the KT boundary. This is just to show you an example. of a orthodontid shark. This is the largest tooth, of the largest lateral tooth of a genus called Cretalamna. Cretalamna evolves into a tortoise, as far as we can tell, and you can see, compare the size of this specimen from the early Campanian, and this is a Danian specimen. You see there's a marked increase in size. It's actually, the increase in size in this lineage is actually a bit more marked than that, because the Campanian Cretalamna are a little bit bigger than the Maastrichtian forms. So if you imagine a Maastrichtian form, about 90% of this tooth. So once you get into the Danian, they have increased rapidly in size. And it just continues that rapid increase in size. And look at this. This is the largest known tooth of Cretalamna of Cretaceous age. And when you get into the Epresian, 55 million years ago, it's huge. So you have basically a situation where for 30 million years, you have sharks, lamniform sharks, growing to 6 to 8 meters. And then you have the extinction of the last of the Cretaceous apex predatory sharks, Cretoxorhina, and the maximum size drops to 3 to 4 meters. And you have big mosasaurs, and then the mosasaurs goes extinct, and straight away these orthodontid sharks increase very rapidly in size because you had a vacant niche. So the orthodontid sharks, they take over the position as apex predators, with Otodus obliquus would have been probably in the order of 10 meters when you get to the Epresian. This is a classic section in Mangishlak in Kazakhstan. This is Coligomine David Ward. And that section in Mangishlak preserves the transition from Otodus to Carcharodon. And Carcharodon eventually produced the mother of all predators. And you can see here, through bed-by-bed collecting, you can see the gradual acquisition here of serration. So it's one of the best documented lineages because they're so large, these teeth. So we have a nearly continuous record from the Danian all the way to the late Pliocene. There were a few attempts by other groups to challenge the orthodontids as apex predator. This is the late Eocene Basilosaurus, a giant toothed whale, could grow to maybe 20 meters, but it was quite elongated, and it wouldn't have been a terribly efficient swim in the open ocean, but maybe in more shallow water environments it would do very well. But it was very narrow. It might have been possibly as heavy as the coexistent Carcharodon, but it didn't survive for long. If you look at whale evolution, they started off at a very elongated shape once they fully adapted to a marine life, very much like the earliest ichthyosaurs. And then as you progress upwards in the stratigraphic column, they attain a more tuna-like morphology, if you like, and the same with the ichthyosaurs. Eventually, the Carcharodon lineage produced Carcharodon Megalodon. You often see speculations, how big could a Megalodon grow to? Well, there are various methods of establishing that. One is to look at the tooth height. Some people look at the crown height. I prefer to try to figure out the jaw circumference, because there is a quite good, strong correlation between the jaw circumference and total body length in modern lamnid sharks, for example. This is from a tooth set from Florida. A virtually complete tooth sets, and if you measure the total upper jaw tooth width here and compare it to, for example, that of a white shark or a mako shark or a porbeagle shark, this particular individual was probably in the order of 12 meters, maybe 11 to 12 meters. And you can then use isolated larger teeth to try to figure out the maximum size of Megalodon. And this tooth, for example, is one of the largest ever found, and my estimate is that it would have come from a shark about 18 meters. I've done this calculation with the number of teeth, and the largest number I come up with is about 19 meters. And at 19 meters, if it was built like a white shark, for example, it would have weighed a bit more than 50 metric tons, maybe 60 tons. Now that's a big predator. That's an enormous predator. This is a classic photograph showing the reconstructed jaw of Carcharocles megalodon. He would have swallowed a mosasaur whole. It would have been like eating spaghetti. No offense to oh dear, mosasaur research here. This is just to give you an idea. They could reach close to 20 meters, that's my opinion, and just to give you an idea about the shark. Imagine facing something like this when you go for a swim. Now, being of such an enormous size, that obviously means you're highly specialized. All evidence suggests that the rise of Carcharocles and its continued increase in size is related to the diversification of whales. When you're 19 meters and weigh 50, 60 tons, there's not much you can eat. I mean, you're big like a submarine. You can't sneak up on a seal, and you would have to eat an awful lot of seals to sustain yourself. So these specialized on whales. There's plenty of evidence where you have big, giant baleen whale vertebrae. They are cut through. Look like someone's cut through with a chainsaw. Megalodon's teeth, they are incredibly thick, and that's obviously needed when you bite into a whale. They seem to have had a bone-crushing dentition, because some of the whale skeletons indicated that if you look at the white shark, when it attacks a smaller whale or the dolphin, they take to go for the soft parts, abdominal parts. But Megalodon tended to just crush its victim. So extremely heavy set of jaws. There were other whales that produced large individuals, the physeteroids, the sperm whales. This is one recently described from Peruvian desert, Leviathan. Could probably grow to maybe 13, 14 meters. It doesn't seem to have successfully replaced Carcharocles, because once you get a diversification of these sharks in the Miocene, but as you get towards the end of the Miocene, you see a reduction in the upper jaw teeth. If you look at the modern sperm whale, it only has functional teeth in the lower jaw. And there seems to be a specialization towards feeding on squid, deep water squid. So what happened to Megalodon? Well, when you get 3 million years ago, we get the establishment of a connection, land bridge between North and South America, with the exchange of mammals. North America gets its first marsupial, I think, since the Oligocene. The Virginian possum migrates from South America to North America, and you get the migration of various placental mammals down into South America, replacing marsupial predators. It appears that the Megalodon just couldn't cope with the onset of the glaciations. For maybe 3, 4, 5 months of the year, its prey just disappeared. It went to the polar, the whales swam off to the polar regions to feed on shrimp, and Megalodon was without food. It appears, all evidence indicate that Megalodon could not adapt to these changes, and they just went extinct. They really set themselves up for extinction. If you only can feed on baleen whales, you know, that's really just doomed strategy. You can see, if you look at Lamniform sharks overall, they did much better in the Cretaceous. If I look at any given time in the Upper Cretaceous, I would say we probably have about 100 species worldwide. But ever since the Cretaceous period, you see a slow but steady decline in diversity of these Lamniform sharks. And today, you have just 15 species left, and they're all highly specialized. You have the white shark, specializes on seals, dolphins in the adult stage. The megamouth shark is a plankton feeder. The basking shark, another plankton feeder. The thresher sharks with this huge elongated upper lobe on the tail. You have the sand tiger shark, which is another specialized species. They actually achieve neutral buoyancy by swallowing air. And it seems like the Lamniform sharks have been replaced by another group of sharks called the Carcharocles sharks. the whaler sharks, like the bull shark or the dusky shark. And they look all very much the same. They are generalists, very generalized in their morphology. And I think, well, by the look of it, it seems like the lamniform sharks are heading towards extinction. They're certainly dropping off in diversity at a fairly steady rate. Now, there's been a bit of speculation in my view, the extinction of Carcharodon is explained by the disappearance of its food source. Some other competing theories have been floating around. For example, one theory is that it was the orcas that drove Megalodon to extinction. I mean, the orcas are big, powerful animals, much smaller than a Megalodon, but they hunt in pack. But if we go back in time to the late Pliocene when we have the last Megalodon and look at the orcas, well, they were a lot smaller. They don't have a tremendously good fossil record, but this is this is an orca from the Pliocene of Italy, Orcanus, I think it's Cytonensis or something along those lines. But the bottom line here is that it was a lot smaller, maybe around 4 meters, and the teeth were also relatively smaller, way too small to handle a Megalodon shark weighing 50, 60 tons. But once Megalodon is gone, the orcas increase quite dramatically in size, and the teeth become relatively larger relative to the size of the animals. So what we see today in the orcas is not what we had back in the Pliocene when the Megalodon was still around. And this is, in contrast, the jaws of the modern orca with much larger teeth and very thick, heavy set of jaws. What happened to the white shark then? Well, if we go back to the Pliocene when the Megalodon, the last Megalodons were around, it appears that the white shark was actually a little bit larger in the Pliocene. You get the transition from smooth cutting edges to serrated cutting edges around 5 million years ago. But the Pliocene, late Miocene examples are a little bit bigger. It doesn't appear that the white shark is rising to the occasion trying to replace Megalodon. It's yielding to the orca by the look of it. So are we left with the orcas? Will the whales now rule the oceans? I mean, this is the first time since the Albion, or 110 million years as we're looking at now, where actually whales are the apex predators. There were a few really large whales in the late Eocene and the Miocene, but we always had the Carcharodon lineage with these humongous sharks. Well, it is possible that we can see a new super predator amongst the Carcharodoniform shark. In the tiger shark in particular is one of the few species that haven't actually shrunk since the late Miocene, Pliocene. Many other lineages of even Carcharodoniform sharks, but Lamniform sharks, they were a little bit bigger if you go back to the early Pliocene or late Miocene. But the modern tiger shark is as big as it's ever been. So it is possible that in the future we will once again see the sharks rise to the occasion, but I doubt it will be the Lamniform sharks. Maybe it's time for the Carcharodoniform shark, like the tiger shark. That basically was my last image. So I thank you for listening to this talk. Thank you.